There's one last topic in section 1.8, and that's difference quotients. This is something that's going to be incredibly important in calculus because it deals with how we're going to be studying functions in calculus. So there's a rather complicated formula for the difference quotient. Rather than just putting it up on the board, I want to sort of talk through where it comes from. So we're going to use it in analyzing a function. So I've got an example up here. We're just going to work with our familiar squaring function, f of x equals x squared. Now if I have an x value in the domain, and of course the domain for this is all real numbers, so any x value will do, that's going to give me a point. And the y value, of course, is just f of x, or x squared. Now what I want to do with the difference quotient is I want to compare two different points on the graph. So I need a second x value. And what I'm going to do is I'm going to call my second x value x plus h. Now what it looks like I'm doing there is I'm letting h, it looks like, represent the distance, the horizontal distance between those two x values. That's almost correct. Now I've drawn this here with h being positive, so that x plus h is to the right of x. H could actually be negative. Your textbook says h has to be positive, and that's just wrong. H can be negative. That's important because we're going to be using this in calculus. And when you get to calculus, h could be either positive or negative. So let's just get used to that now. Totally fine for you to choose to draw your pictures with h being positive, because that's certainly simpler to work with. If h were negative, x plus h would simply be a point to the left of x. By allowing h to be signed, we can choose a second point on either side of x. Okay. So what we're really letting h be is the signed distance. So distance is always positive. If h is negative, it's just the opposite of the distance. And it's telling us then when it's negative, x plus h is on the left. When h is positive, x plus h is on the right. So the sign tells us which side of x we're on. The absolute value tells us how far away from x we are. So it's the signed distance between our x values. Now, if I have this other point here, that's going to correspond to a point on the graph whose x value, whose input is x plus h. Now, if I were to calculate my y value, that means I'm plugging in x plus h as my input, and so we're going to get that input squared. So it would be x plus h quantity squared. So I've got one point whose input is x, and one point whose input is x plus h, a point that is h units away, the absolute value of h units away from x. Okay. All right, and generally h will be a small number, although in theory it could be a big number as well if I wanted points that were really far away. Now what I can do, once I have 2 points, they determine a line. That line we call a secant line. Now you've seen the word secant before in a trigonometric context. This does have something to do with that trig function, but honestly at this point in our math career, I think it's easiest to simply think of that as we're using the same word in a different context, because the connection to the trig function isn't really relevant to understanding what this means. So it's probably more useful to just think of it as one of those times where we use the same word to mean two different things. So a secant line is just a line connecting 2 points on the graph of a function. That's all it is. Okay. Now, if I were to calculate the slope of that secant line, I know that slope is just rise over run. And I can calculate both of those by just subtracting. So the rise I can calculate by subtracting my y values. Now it doesn't matter whether I start here and subtract these values, or start here and subtract these values, as long as I'm consistent. Whatever point I start with, I've got to start my subtraction problem for the rise and the run at that point. It's generally simpler if we start with the more complicated point. So for the rise, I'm going to take this y value minus this y value. So that would be x plus h squared minus x squared. And then for the run, that will be this x value minus this x value. So x plus h minus x. Now notice that denominator simplifies really nicely. Now the x's cancel and the denominator is just h. So we've got x plus h squared minus x squared all over h. That's the slope of this secant line. Okay, now if I had subtracted in the other order, so that on top I had x squared minus x plus h squared, I could do that, but then on bottom I wouldn't have just h, because I'd have x minus the quantity x plus h. I'd have to distribute that negative and I'd get negative h. So it's definitely much simpler to start your subtraction problem at the point that has the h in it. That way the run is just h. In fact, that's how we define run. It's the signed distance between our x values. Okay. All right, so the slope of the secant line is this thing, and that is the difference quotient. The difference quotient is the slope of the secant line between 2 points, one point whose input is x and one point whose input is x plus h, a point that's just a little bit away. Okay. Now, why is that so important? Well, what that does is that tells me how the function is changing. Okay. Because lines have a slope, right? And this line I can see is going up. It's going to have a positive slope. Okay. Now I can see this function is increasing on this interval, and that's going to be captured by the slope of that secant line. So it's easy to talk about the rate of change of a line because it's the slope. What the slope of a secant line gives me is the average rate of change of f over this interval that has x and x plus h as its endpoints. So it's going to be a way of figuring out how is my function changing. If my function were something like a position function, position as a function of time, then that rate of change would be the average velocity. Okay. So there are lots and lots of applications in math and in the sciences where we're concerned about how fast something is changing. And the difference quotient is going to give us a way of calculating an average rate of change over a time interval. Now, that's what we're going to do this semester. In calculus, what you do is you then look for a pattern as you make h smaller and smaller and smaller and smaller. And if you can notice a pattern, then you can move from talking about the average rate of change over a time interval to the instantaneous rate of change. How fast is the function changing right now at this very moment in time? That's what you'll be doing in calculus. In pre-calculus, we've got to get this skill of calculating the average rate of change. Okay, so that is our definition of a difference quotient. I'm going to just write it out in its generic form here. We've got a specific example for x squared. In general, if I have some function, I'm going to have a point x, and then the y value would be f of x. And then I'll have a point x plus h, and the y value would be f of x plus h. Then we can draw in that secant line, and the difference quotient is just the slope of that secant line. So it would be f of x plus h minus f of x, that's my rise, over h. X plus h minus x is just going to give me h, which is the run. Okay. All right, so if I just gave you that formula, it sort of feels like a mouthful. But if you recognize that it's just the slope of this secant line, this formula amounts to just rise over run. So that makes it, I think, a little bit easier to remember. All right, let's actually see if we can't now simplify this. So this is the difference quotient, but you'll usually be asked to simplify it. So if I wanted to work this out, I need to remember that for x plus h squared, that means x plus h times x plus h, and then minus x squared all over h. So that exponent does not distribute over addition. I'm going to need to FOIL this out. Now if I do, I'm going to get x squared. Outsides and insides each give me an x times h. So that's going to give me 2 copies of x times h. And then last terms will give me h squared. Then minus x squared all over h. Okay. Now, at this point, I can't cancel my h's because I don't have an h in every single term. But if I look, this x squared and this minus x squared will cancel each other out. So this is going to become 2xh plus h squared over h. Now there's an h in every term on the top, so I can factor one out. I can't cancel just those or just those. I've got to be able to cancel with the entire top. I can do that if I first factor out an h. So if I factor out the h, I'm left with 2x plus h all over h. Now this h is connected to the rest of the top by multiplication, so I can cancel it. I do, however, want to be careful because from the beginning we've had h in the denominator. So I can see that h can't be 0. If h were 0, I wouldn't have 2 points because my second point would be the same as the first, and then I couldn't calculate a slope. So I understand geometrically why h can't be 0, and algebraically I can see that it can't be 0. Now if I just cancel these h's and I write 2x plus h, it sure looks like h could be 0. Anytime you're simplifying and you remove something from the denominator, you still have that restriction that h cannot be 0. So when I simplify the difference quotient, what I get is 2x plus h with the restriction that h isn't 0. Now, I'm going to require that you write that. The book does not write that every time. So here's what I promise to do. On any work that I assign you, I will remind you. So I will say, find and simplify the difference quotient. Remember to record any restrictions on your variables that are not otherwise clear from your answer. So as long as there's an h in the denominator, I can tell that h isn't 0. As soon as I cancel it, I've got to explicitly record that. And I will tell you right now, when you're simplifying a difference quotient, you should always be able to simplify to the point that you're able to cancel the h in the denominator. Okay. Now, if you can't, let's say I had a term here that didn't have any h's in it. Don't make up math and start canceling anyway. Check your work. You should be able to get to a point where you can factor out an h on the top. But you've got to be able to factor it out from every term on the top before you can cancel it. Okay, so that's just, I'm sort of giving away that you should always be able to do this so that you'll pretty much always have to record that h isn't 0. And I will remind you of that, but I will require that you do that.